don't know. That seems like. Yeah, I know, I was like, oh. Yep. That's an excuse.
All right, guys, all right, let's stand up, let's stand up, stretch. We have what due tonight at 11:59? WebAssign, okay, let's sit back down. We have what next Friday? A quest. Okay, our fourth quest, or third quest, right? Fourth quest? Okay, our fourth quest. Not real good with integers. And then we're gonna have one more quest. We're gonna have one more quest before break. And the only way to do that is it's the Friday before break. So make sure you leave after your quest on Friday for break. And it'll be the last time I see you physically until spring, okay? Okay, we've started what I consider the hardest content. We've started what I consider the hardest conceptual content of the course. You're not going to think it's the hardest. You're going to think integration's the hardest, or some of the stuff that we do later in the chapter. But I'm telling you, it's the hardest. We're defining what it means to be a limit of a function that depends on more than one variable. Now we're almost going to exclusively hang in this class where it's just going to be a function of x and y. Because if I can't understand it for 2, I don't need to go to 3 or higher. At least when it's 2, I can talk about the graph of it. If I say a plus td, you say, if I say r of t, you say space curve. Okay, if I say z equals f of xy, I want you guys to think space sheet. You know, and so I've got something here, we can imagine that, we've got this thing. David, just hold it there. And maybe we've got, right now I ain't a function. Okay, there we go. So we can imagine that we've got something like this. It kind of spins like that. My domain is the floor. I pick an x and y. I come up, I shoot over. Maybe my z-axis is over there. Does this make sense? So when I say z, thanks, David. When I say z equals f of xy, I want you guys to say space sheet. Okay? Sitting up there in 3-dimensional space. Now, calculus is about limits, derivatives, and integrals. Oh my, okay? And so we would imagine that if we're going to extend the concept of a derivative, rate of change, to higher dimensions, do you think it's going to be dependent on a limit? And unfortunately, the kind of limits we talk about aren't the ones we like. They're the limits where the denominator goes to 0 and the numerator goes to 0. They're the hard limits. We've got to come up with clever ways to evaluate them. We read this like this, the limit as x approaches a. And that's the way we visualize it, even though the limit is not defined that way. We say as x gets closer and closer to a, in the domain, f of x is going to get closer and closer to L in the range. But math is proof. There's nothing that we can define for closer and closer. Well, Dr. Warren, you get closer and closer. What the hell is that? What do you mean closer? Well, you keep getting closer. As soon as you see how you can't prove a damn thing with that. This, however, we can prove. As much as we don't like it, we say this is true if and only if you give me an error tolerance, you give me an epsilon, an error tolerance for the range, I can find another error tolerance in the domain where if I start in this circle, like Dr. Warren, that's a circle? Yes. It's a circle whose center is, from what we learned last time, it's a circle whose center is A and whose radius is delta. If I pick an x in that circle, if I pick an x in this circle, I choose an x in this circle where that vector's norm, that vector x minus, I know English is coming, where that vector x minus a's distance is less than delta. I just got to ask, guys, is the distance in there, the way I drew it, is it less than delta? If I pick that and I evaluate the function at that point, then its range value, f of x, the distance between it and L must be less than epsilon. It must fall within my error tolerance I set around my limiting value up there in the range. Now the kicker, the thing that makes it closer and closer, the thing that makes it a real definition of closer and closer is that word right there, which means for every. So as I squeeze in, if I make my error tolerance tighter, make that epsilon smaller, what has to happen down here in the domain? What has to happen with that delta? It's got to shrink. That circle is going to shrink around there. And as I keep going in, epsilon's any positive number, I keep making that circle smaller and smaller. And so this is what we're saying. As you squeeze in around L, it's forcing you to pick points closer and closer to A. And this is something that we can actually define stuff in terms of. This is an actual honest definition that we can prove stuff in terms of. The problem is, it's a pain. It's really hard to prove stuff with this definition. Most of the time in 237, I make about 4 or 5 really important arguments, but not during COVID, okay? I'm gonna give you stuff for free. Okay. This is what comes to save the day. And I want to take you back to 235. Imagine that you're looking at this function here. What kind of function is this? Let's go back and make your high school teacher so proud of you. What kind of function is this? Piecewise defined. Very good one. It's defined in terms of pieces. I kind of think of it as a Frankenstein function. Whenever I see this brace, I'm always like, oh crap. It's a piecewise defined function. It's going to be hard. It's pretty easy to spot. It's going to be hard. Just like Frankenstein. If you saw a big green guy, 8 foot tall, green with scars all over its body and electrodes sticking out of its neck, you'd be like, I think I'm gonna step to the other side of the sidewalk, let that guy go. You know it's Frankenstein or a drunk JMU student at Halloween. I mean, you're not really sure, but you would be aware. Now suppose I'm taking the limit of this thing. You're like, well, it's not bad, Dr. Warren. As long as you don't take the limit where it's sewn together at, it's easy. Continuous, easy to take limits. You're like, God damn it, Dr. Warren, you're taking the limit exactly where it's sewn together at. Now, how do we do limits like this? How do we evaluate limits of Frankenstein functions at the value where they're sewn together at? Does anybody remember? What's the only way you can do limits when they're like this? Keep walking back and forth. You're like my daughters. He'll give up. He'll tell us. It's like when I say, could somebody clean the van? Could somebody go out and just clean the van? And you guys don't even have to clean it. You just gotta clean your crap out of the back pockets. How many people have been in a minivan before? How many people's parents had a minivan? How many people shoved their crap down in those pockets? Gum. I mean, I don't even know. I can't even imagine. When I stick my hand down in there, it's sticky when it comes back out. I'm just like, what have you left soda bottles in there? Candy wrappers? I mean, I know, like, whoever said sugar and spice and everything nice, that's what little girls are made of, didn't know my girls. They have farting contests. I'm like, seriously guys, we're in a van, we're gonna have farting contests? Belching contests. Okay, well enough. All right, here we are, back to here. How do you deal with things like this? Left and right, very good, Cameron. One person, the left and the right. Do you guys remember having to take left-hand limits and right-hand limits? And so if we were looking at this, we would explore this coming in from the right, but then which of our two branches would you be using? Would you be using the x squared or the x plus 2? X squared. This is continuous, so I can evaluate this super easily by just plug it in, and I get the number, just plug it in, you get the number 9. Now I look at the limit as x approaches 3 from the left of f of x. Now which branch am I on? Now which branch am I on? X plus 2. Again, this is continuous as a function. Plug it in and I get 5. What does that tell me about my limit? What does that tell me about my actual limit at 3? It does not exist. If the limit from the left doesn't equal the limit from the right, then the limit does not exist. Okay, your BFF, your best friend forever, should be in your phone. In your mathematical phone. So pretend you're pulling out your mathematical phone. Pull it out. Okay. Let's enter the function. Let's enter our number. F is continuous at C. Write down what it means. Draw, what does it mean when you say, what's the definition that a function is continuous at C? Because that's your BFF. In analysis, there's no better friend than continuity. Except differentiability, but we rely heavily on continuity for differentiability. F is continuous at C if and only if what? And you should have it down by now. Because it should be bam, done. Definition. F is continuous at C if and only if what? 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 Calculus is about, it's defined in terms of a limit as x approaches C. You're like, Dr. Warren, it's not the derivative. No, there's no fraction. F of x equals f of C. F of x equals f of C. If you had to guess, and we jump up into higher dimensions, what do you think our definition of f being continuous at x equals a? If you had to guess, take a guess, guys. What do you think our definition is going to be for a function being continuous at a? Well, calculus is about limits, derivatives, and integrals. So it's going to be defined in terms of a limit. And you're like, well, I don't know, Dr. Warren, how about the limit as x approaches a of f of x equals f of a. And that's exactly what it is. And this is your BFF. This is your BFF. Let's first of all try to understand it graphically. And we can kind of see it up here. This is a continuous space sheet. Does that make sense? I mean, do you see there's no holes in my sheet? Do you see I have no holes in my sheet? There's no singularities. I mean, guys, aren't singularities cool in higher dimensions? Like, what do they look like, Dr. Warren? Like black holes, kind of. Matter's being sucked into them. Singularities. Say that. Yeah, imagine these big, huge things spiking up forever and ever and ever. Does it look like I have a singularity at A? Does it look like I have a singularity at A? And the answer is no. If I just plug my A in, this is kind of like my f of A. Does it make sense that as I shrink epsilon down and my delta squeezes in here, that the f of x values will get closer and closer to f of A? Does that make sense? As I squeeze in here, does it make sense that my f of x values will get closer and closer to f of A? And so I'll meet that definition. Like, Dr. Warren, I'm not getting it. Why is it my BFF? Well, gosh. One reason is, is it hard to evaluate limits if they're continuous? If the function's continuous, is it hard to evaluate the limit at A? You just plug it in. So say that. Get your hands in the air. Okay, so if the function's continuous, some of you guys didn't have your hands in the air. The function's continuous, then you can evaluate the limit by just plug it in. What do you mean, Dr. Warren? Just plug A in. Now, I'm going to let you guys off the hook. I'm just going to give you this. As long as your multidimensional function doesn't have one of those. Okay, right? What kind of function is that? What kind of function is that? Piecewise, a Frankenstein function. As long as it's not piecewise defined, which in this class it's not going to be very often, or it's not got one of those, which is a fraction, and it's not functions that we know, like natural log has some problems. Natural log has some problems. As long as it's in the domain, you can assume the function's continuous at that point. And if you're asked to evaluate a limit, you just plug it in. So let's do our first limit problem. Let's do our very first limit problem in higher dimensions. Now, I'm terrified of this section because writing problems can be a nightmare. So for the first time this semester, I brought my textbook. First and likely last time of the semester, I'll bring my textbook. So let's look at a limit. So we're going to take the limit, and I'll just tell you which problem this is. It's problem number 6 in section 14.2. It's problem number 6 in section 14.2. And they don't use vector notation, so I won't use it either, so we match up. I'm taking the limit as xy approaches to -1. And my function has a fraction, which is disappointing. It's x squared minus y squared on the bottom. And on the top, I've got a x squared y plus a x y squared. And what it's asking is, does the limit exist? And if it does, what does it equal? So what are we trying to answer? What are we trying to answer? Does the limit exist? And then what does it equal? Okay. If you're talking about the domain of this function, are there any problems? If you're thinking about the domain of the function, is there any problems? We don't ever want x squared to be equal to y squared. So if I'm thinking about the domain of this piece, I don't ever want x squared to be minus y squared to be 0, or x squared to be y squared, which would mean y would be equal to plus or minus x. Y would be equal to plus or minus x. And you're like, Dr. Warren, what does that really mean? Well, remember, guys, this is a multidimensional function. Where's the domain? This is a multidimensional function. Where's the domain? In the xy plane. Very good, Dave. So if I'm thinking about graphing the domain here, Z's my range axis. There's my two domain axes. What's y equals x? What's y equal x look like down here? What does y equals x look like down here? A line. A line. It's gonna kind of run through here like this. So none of those guys are allowed. None of those guys are allowed. And who else? Who else is not allowed? Anytime y equals negative x, but that's also that graph is also a line. It just runs this way. And so as long as you're not on that line, you're in the domain and you're continuous at that point. Now look at the point they gave me. What's the point they gave me? 2, -1. Is 2, -1 on either one of those lines? Is 2, -1 on either one of those lines? So in this class, because it's in the domain, we can just use continuity. If as long as it's in the domain, it's going to be continuous in this class. Is it hard to evaluate limits? Is it hard to evaluate limits when it's continuous? And the answer is, you just plug it in. So let's do that. Let's just plug it in. So wherever I would see the x, I'm going to put a 2, and wherever I see a y, I'm going to put a -1. So it's just going to be 2 squared times -1 plus 2 times -1 squared all over 2 squared minus -1 squared. Now, because I've taken away your calculator, guys, you're done. At that point in time, I don't need to know the number. I don't need to see you make arithmetic mistakes. Okay, if you're doing a test, some of you can't help yourself. You'll be so driven to look at the answer in the back, you'll have to actually evaluate that. But I'm telling you on a quest, you can stop right there. You're showing me you understand the calculus. Now let's change the game for a moment. Suppose I ask that. Is that different? Is that different? Is that different? Because now the numerator would go to 0 and the denominator goes to 0. And then suddenly, I've lost my good buddy continuity, and I don't know what to do right now. I don't know what to do. Here's another thing I'm going to let you have. I should prove it, but I'm not going to. I should not. I'm giving you this as a present. Okay, this is a gift. If you have a fraction and you're taking the limit of a fraction, the limit of the division, the quotient of two functions. This is a present. If the numerator goes to a number that's not 0, if the numerator goes to a number that's not 0, and the denominator goes to 0, I'm going to let you just, by waving your hand, say that limit does not exist. If the numerator goes to something that's not 0, and the denominator goes to 0, you can immediately say, finish your question on the quest by just writing D N E. Let me give you an example of that. Suppose we were looking at this limit. Suppose I was looking at this limit. Who's the A? Who's the vector A that we're looking at? Who's the point there? Who's the point? Who's the point? -2, 3, okay? Now, when you're looking at the top, where does the numerator go? Where does the numerator go? Since there is no y, I'm only concerned with the x. Where does the numerator go? 4. Where does the denominator go? 0. So at that point in time in your homework, at that point in time on the quest, you can immediately finish the question by writing do not exist. How many people like that? How many people like that? How many people like that? So imagine you were looking at this. Suppose I'm looking at the limit as x approaches y of 2, 2 of x squared plus y squared. Suppose I want to calculate that limit. Suppose I want to calculate that limit. Suppose I'm looking at that limit right there. Is there any division? Is there any division? Is there any division? Is there any division there? Is the function continuous? Is the function continuous? Then how will you evaluate the limit? How will you evaluate the limit? Just plug it in. What number would you get? What number would you get, guys? What number would you get when you do that? 8, and if I ask for a justification, you could say, by continuity. Done. By continuity. My BFF. Okay, let's see what you remember from Math 235. F prime of C, by definition, is equal to what? Write down. By definition, F prime of C is equal to what? F prime of C, Math 235, Calc 1. Okay, Math 237, space curve derivative. Vector R prime of C is defined to be what? This is one of your flashcards. R prime of C is defined to be what? Okay, let's see what you got for me. Michael, what do you got for F prime of C?
So x goes to c, and I said f of x minus f of c, and I think it's over h or f of c minus.
H works in some things, but it's not H here. It's X minus C. X minus C. How about R prime of C along the space curve, guys? How about R prime of C along the space curve? What's that equal to? The limit as C approaches C of R of T minus R of C divided by T minus C. Derivatives are defined in terms of, I don't know what Dr. Warren, I can't focus at all. Derivatives are defined in terms of, derivative is defined in terms of limits. Okay, look at this derivative. Is it defined in terms of a limit? Where does the denominator go? Where does the denominator go? 0. Here's another derivative. Where does the denominator go? 0. Where does the numerator go? Well, x goes to c, you get f of c minus f of c, which is 0. T goes to c, r of t minus r of c is 0. Guess what happens when we go to higher dimensions? Guess what happens when we define a derivative in higher dimensions? It's going to be defined in terms of a, it's going to be defined in terms of a, it's going to be defined in terms of a limit, and do you think it's going to have a denominator? And guess where the denominator is going to go?
0.
And guess where the numerator is going to go? 0. So even though when you're doing any limit section, I know nobody will listen. I'm only going to talk to my buddy, the iPad here. iPadders, look at me. Whenever you go to any limit section, they always have these limits of 0 over 0. And they always seem obscure. They're always like, this is kind of a bizarre case. This doesn't have any merit. They're just trying to beat me up. They just want to make it hard. And then somehow, I went through all of undergrad and got to grad school. And I didn't know that a derivative was defined in terms of a limit. How bad is that? If you ask me what a derivative was, I said it was the slope of the tangent line. It's the velocity. That was my understanding. I never got it was defined in terms of a limit. Not only that, it's a 0 over 0 limit. I'm like, well, Dr. Warren, I don't want to make delta epsilon proofs. Say that. I mean, let alone 0 over 0 epsilon proofs. It goes to L. I have an L plus epsilon and L minus epsilon. Go find delta. How many people realize they don't want to do that? How many people are like, I don't want to? for the sake of God, don't make me do that. I mean, how many one of us like say that almost? In every other semester, I make kids do delta epsilon proofs. But you happen to be in the 2020 COVID 237, and you're not going to have to make a single delta epsilon proof. I'm going to prove one. I'm not even going to prove. I'm going to heuristically wave my hands. This is something that I need. It's this, that if the limit is 0, if the L is 0, the limit as x approaches any a of f of any function x, vector x, goes to 0, this is true if and only if the limit as x approaches a of the absolute value of that function also goes to 0. This is something that I'm going to need. That if the absolute value goes to 0, then the function goes to 0. If the function goes to 0, then the absolute value of the function also goes to 0. Do I have any math majors in here? Do I have a single math major in here? I guess they, okay, 2. Okay, whenever you guys see this, whenever you see that in a theorem, if you're a math major, you're like, you just want to puke into your mouth at that point in time. You're just like, especially on a test, you're like, you gotta be freaking kidding me. Because when you see this, they don't just want you to prove it this way. They want you to prove it that way. It's really two proofs. And you know, like, if I screw this problem up, I'm toast. When it's given to you, like I'm giving it to you, you're like, hallelujah. I can either start here and immediately go there, or I can start here and immediately go there. Now I'll try to justify this for you. Let's go back to our definition. You give me an epsilon, there has to exist a. Give me an epsilon, there has to exist a delta. So imagine that I'm starting here. Then I know for some arbitrary epsilon, there's going to be a delta. I know, give me any epsilon, there's going to be a delta where if I start here, I can get where? Using the definitional limit. Like that one, I have no idea what to write down next. If you start here, let me ask you, do you guys see this anywhere else in the room? Just asking, do you see that anywhere? Robert's like, over there. So let's just see, what's on the other side there? Absolute value of f of x minus L. Now who's my L now? Who's my L? 0 would be less than epsilon. Give me a different epsilon, there's going to be a different delta where I can start here and get there. Okay, now I'm going to ask, if you just look at this, guys, if you just look at this, is this not the same thing? Is this not the same thing as that? If you did this, is it not the same thing as that? Would you get the same thing if you did that? Would you get the exact same thing? And so we see here, the delta that works for this guy is also going to work for that guy. Or vice versa, the delta that works for this guy is also going to work for that guy. And that's kind of a wavy hand heuristic argument for why this works. Fortunately, you'll probably use this 3 times in this class. You'll probably use this 3 times in this class on quests. Twice maybe next Friday. Probably twice maybe next Friday. Or once. Okay, stand up, you're going to need it. Stand up. Stretch. Look at somebody and say, this is gonna suck. Say, this is really going to suck. Okay, sit back down. Okay. Does everybody agree I'm like 60 away from everybody? Does everybody agree I'm like 60 away? Okay, so I'm taking off my mask because I want you to see my face. Guys, this is going to challenge you. This is going to challenge you. But the alternative is to use the delta epsilon definition. How many people don't want to use the delta epsilon definition? So I'm going to define a domain curve. And then I'll explain why. This says definition. A domain curve, and I'm using a script C, so it doesn't get confused with anything else. The domain curve C at x equals a. So I'm defining what it means to be a domain curve at the point x equals a. A domain curve is a set of vectors, or we think of them as being points. It's a vector valued function, say that. Fortunately, have we been working with vector valued functions? Have we been doing quite a bit with vector valued functions? Now, because it's a domain curve, we're typically going to think of it as x of t and y of t. We're typically going to think of it almost exclusively in this class as x of t and y of t. And so if I'm thinking about down here in my xy plane, it's going to be a curve. It's going to be a curve running down in my xy plane. So here we are. C is the set of R of t where they're such that there, what is that word? That word, I'm late. Such that there exists a t. Oh gosh, I made a mistake. Sorry. That's supposed to be a C. My bad. That's supposed to be a C. So if you've already copied it down, go back and change it. That's supposed to be a C. I don't know how you learn anything from me. Such that there exists a C, an element of the reals, where R of C is equal to A. And that's what we mean a domain curve at A. There's some C value. There's some C value where the curve runs through A. So if I back up here, well, I guess I erased it. So imagine that I've got a vector A here down in the domain. This R of t at some value of C, if I'm running along this curve, there's some place where that curve actually slams into that vector A. Or we will almost exclusively work with this. But you can also be a domain curve as long as the limit also at C goes to A. Even if it's not defined at C, it's still okay. It's still part of the domain curve. But we'll almost exclusively work with domain curves that look like this. And I talked to one, why are we defining domain curves? Why are you doing this to me? Because you don't want to deal with this. You don't want to deal with that. Okay. Here's the definition. Let me read. Definition. Now, you guys, I know this is hard, but you guys start reading. The limit as x approaches A. How many people are comfortable so far? How many people like got that? You're just like, what the hell is this? What's this extra thing down here? Well, it's a domain curve. The limit as x approaches A along the domain curve C. Now say that again. As A along the domain curve C. Say it again. Along the domain curve C of f of x is equal to the limit. Now notice the game switched on us. It's no longer an x, but now suddenly we're dealing with a, it's no longer an x, but now we're dealing with a t. And we no longer have a vector A, we have a scalar C, we still have our f, but now it's not f of x, but it's f of r of t. That's the definition of what we mean to take a limit along a domain curve. You're like, Dr. Warren, why would I even care? Because when you see this, this is multidimensional. This is multidimensional. Delta epsilon. When you see this, it's math 235. Do we have a L'Hopital's rule? Do we have a L'Hopital's rule in math 235? Have you taken limits in math 235? You know factoring's important. You know factoring's important. You know some other things are important. However, here, we've got no machinery built, just our definition. We have no machinery built, other than our one little theorem with the zero. Okay. This is the theorem that comes and saves the day. The one over here is the theorem that comes to save the day. This is the theorem that'll help you avoid almost ever having to deal with delta epsilon in this class. And again, it takes a day to prove it. It takes a day to prove this theorem. But it says this. Read. Theorem. You're like, oh crap, we gotta prove it. You like definitions. We just get to accept it. Okay, I like to think of definitions as being like the Constitution, the U.S. Constitution, which is getting violated all the time now. Oh, okay. Constitution. Theorems are more like things you have to prove. These are more things that you prove based off of your Constitution. Okay, so I'm disappointed, and I'm extra disappointed because it's a if and only if proof, which means you have to show it. Emily, you've got to show it that way, and you got to show it that way. And this is why it takes an entire lecture to do it. So now read it to me. Let's make sure we can at least read them here. The limit as A of equals L. You can say if and only if. Now let's see how well you do this. As x approaches A along the domain curve C of f of x equals L, and this is the thing. For every domain curve C at A. So if along every domain curve, I don't know why I think if I say it that way, just say it nice and monotone. Use an acting voice, they'll understand. Along every domain curve, as long as the limit along every domain curve is, L, then the limit goes to. If the limit goes to L, then the limit along every domain curve goes to L. And like, what the hell's a domain curve? Oh, weren't you paying attention? It's a vector value function that hits A. Well, what do you mean by running the limit along a domain curve? Well, you just plug in the x of t and your x of t and your y of t and take the limit as t goes to that c that we have there. Now ask me, Dr. Warren, when will we use this? When will we use this? Write this down. Write this down. Most of the time you use this when you have a 0 over 0 limit. So when's most of the time we use this? 0 over 0 limit, and most of the time we use it to show a limit does not exist. What did I say? So most of the time you use this when you have what kind of limits in higher dimensions? 0 over 0, and most of the time you use it to show that a limit does not exist. Does not exist. And then there are other times we exploit it. If they tell you the limit exists, you're like, hallelujah. If they tell you it exists, if that's part of the theorem, you're like, hallelujah. Then every single limit along every freaking domain curve also has to go to that same number L. So you can use it like that as a lever, a huge lever. However, in 14.2, most of the time you're using it to show that a limit does not exist. Okay, so now I'm going to do that. I'm going to show you. Now, guys, this is challenging. Most of the time you want things, Dr. Warren, give me some kind of procedure. I got none. I've got none. I brought the textbook for the first time because I'm afraid to make up a problem I can't do. That doesn't happen often, but I'm afraid I'm going to make up something that I'm going to spend 20 or 30 minutes of class trying to figure out if the limit does not exist or does exist. Now the book does this pretty easily for you. It makes life pretty easy. They only look at limits. They only look at limits that go to 0. And they're looking at limits that go to 0 over 0. Okay, so if the limit doesn't exist, it's going to go to 0 and it's going to be a 0 over 0 limit. Sometimes it does exist, sometimes it doesn't exist. Okay, so now I'm going to look at a limit that is a 0 over 0 limit, and I'm going to show you guys how to show it does not exist. Okay, so not only that, I'm going to pick one from your textbook. It's a lot like your homework. It's a lot like your homework that I put up for this. So here we go. What can I erase? Who's your BFF? Who's your BFF? Who's your BFF? Who's your BFF? Continuity. As long as there's no division by 0, how do you evaluate the limit? Stand up again. You need this. And I want no complaints. I want no complaints. Or else I'm just going to lead you to the wolves, delta and epsilon. Okay, sit back down. This is saving you from delta epsilon. I kind of view it as the Beast and Beauty and the Beast. Okay, I kind of view it as the Beast and Beauty and the Beast. Anybody see the movie Beauty and the Beast, the cartoon, when you were a child? Okay, so do you remember, like, when you first see the Beast, you're like, oh my gosh, this horrible beast. And that's the way domain curves feel. Okay, but then you think about the wolves that were eating at the delta and epsilon. And you're like, oh, thank goodness for the beast. And you find out domain curves are really a really nice friend to have. So let me pick a question. I almost wrote one down. I know better though. I've been burned so many times. Let me pick this one maybe. Okay, yeah, let me do the limit. And like I said, the book's kind of lame. Because when they look at 0 over 0 limits, they just go to 0. Okay, so we're looking at this. Is there a fraction? So next Friday, if you're doing one of these, first thing you see a fraction, you're like, oh crap, it's a fraction. As long as the denominator doesn't go to 0, I'm in good shape. Well, guess what happens? Plug it in, what do you get?
0.
You're like, oh, if only the numerator doesn't go to 0, I'm in great shape. I can get this problem done in no time. But when you plug 0 in, 0 in, what do you get? 0. And you're like, oh crap. Now comes the hard part. Your instincts have to tell you, do I think it exists or do I think it not exist? And that's sometimes hard. If I'm looking at the numerator, it's roughly a 4th degree, and I'm not sure about that guy. But I do know as x goes to 0, cosine of 0, I know, I'm not sure you know, cosine of 0 is 1, so that's not helping drive it to 0. If this was sine squared, it would be very different. So the degree's about the same, and I've got this plus down here. Now because I'm old, I'm almost 60, months from being 60, I've done this a few years. My instincts tell me, I don't think this limit's going to exist. That's just my instinct. It's not going to exist. It's not easy for me to even determine that. And you're like, well, how could I possibly show this limit does not exist? Somebody goes, well, let's use the definition of limit. And you're like, hell no, we're not going to do that. Let's use domain curves. Let's try to find two different domain curves that go to different numbers. If we do that, then the limit does not exist. And like, well, Dr. Warren, what's the analog of that in Calc 1? What's this? In Calc 1, you got a C. Your domain is an axis. What did I just say? I've almost beaten the hell out of you to the point where you're almost sound asleep. You can only approach C this way from the left, or you can approach C from the right. But down here, when my domain's jumped up to here, and I've got A, how many paths are through A? How many directions can you come into A down there? Think about Rome. Could I come in this way? Could I swing in that way? Could I ride a line in that way? Do you see how there's infinitely many paths to approach this? And that's the analog. We're using, say this, one-sided limits. We're essentially using one-sided limits up a dimension. We're taking two different paths. We're taking two different paths through the point A. The easiest paths, the ones I first try, are these guys. My first domain curve, I let be R of t equals t0. Now I've got to ask, is this a curve that would actually hit 0, 0? Is this a curve that would actually hit 0, 0? What would C be? If I want R of C to be 0, 0, what would C be? What would C be? 0. So there's my C, which I need from my domain curve. Okay, you don't need to do this on the quest. You don't need to do this on homework, but draw that domain curve. Draw the domain curve down there in the xy plane that represents t0. Draw the domain curve t0. See if you can do that. Draw the domain curve t0. I'll help you here. Who's A? Who's A? Who's A in this problem? Who is the vector A? Who's the A in this problem? Who's the A? 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 0, 0. So it's that point right there. Okay, now if I look at this, x of t is equal to what? X of t is equal to what in this case? X of t is equal to what in this case? T, and y of t is equal to what in this case? 0. 0. So y is always 0. So I know y is always 0, and x is t. So what am I going to get, guys, when I do that? A plus td. A line. I'm going to get the line along. I'm going to get the line along the x-axis. Now let's evaluate this limit along this space curve. Let's evaluate this limit along this space curve. So I would have the limit as xy. I know no matter what words comes out of my mouth right now, it doesn't matter. I'm going to run Pocahontas along the Appalachian Trail of Mickey Mouse. And then you heard as much as you were hearing now. Okay, so now I'm looking at that. What does this mean? What does this mean? Read it to me. The correct way, read it. Limit as xy approaches 0, 0 along the space curve C1. Where is that defined? Where is that defined in the room? Where's the limit along a space curve defined? Where's it defined, guys? It's defined right here. Who's your x of t in this vector value function? Who's x of t? Who's x of t? Who's our x of t? Who's our x of t? Who's our y of t? 0. So this would be the limit as t approaches who is our c? Who is the value of c we needed to be a domain curve? 0. So it's going to be the limit as t approaches 0 of f of t 0 of f of t 0 f of r of t. So wherever I see the x, I'm going to put a t, and wherever I see a y, I'm going to put a 0. So I would have a 5t, the limit as t approaches 0. Now you guys help me out. What are we going to have in the denominator? What are we going to have in the denominator when we evaluate that? What are we going to have? We're going to have a t to the 4th, and for your notes, I'll put that in there. You'd never do that on a quest. And then I'm going to have a 0 to the 4th, and then a cosine squared of t. How many people are following? How many people are following? How many people are at least getting some grasp of this? Now let's do a little bit of algebra. Clean this up. Now we're in 235. Now this is back to Calc 1. I'm looking at this limit as t approaches 0. What do we get in the numerator? Let me just do a little bit of algebra. What do you get in the numerator, guys? 0 over t to the 4th. Like Dr. Warren, where's this going to go? Well, any number times 0 is 0. And so this is equal to the limit as t approaches 0 of 0. Because t never gets to 0. This will always be 0. What's the limit of 0? What's the limit of 0 from Calc 1? 0. You're like, Dr. Warren, so the limit's 0? No! The limit along this space curve is 0. There's one path. Where we have a number. We got the number 0. If I can find another path that doesn't go to 0, what can I say? If I can find another path where the limit doesn't go to 0, what can I say? It does not exist. It does not exist. Okay, so there's 1. We've got 1. So you guys help me out. What do you guys think? What might be another space curve that we could use? What do you think another space curve we could use to take a look at and see what we might get? What do you guys think? What could be another space curve? Michael? T1. Now I've got to ask, will there be a C? Is there a C that I can plug in here to get 0, 0? Is there a C that I can plug in to get A? Is there a C that you could plug in here to get to the point 0, 0? And the answer is no, because this guy's always, and it'll never be 0. So I like it. I mean, Michael's at least shooting. Some of you guys are just gone. You're comatose. Another try.
0 t.
How about, like I want you to use that one up. Have we, or is this a different space curve than this one? Is this a different space curve than this one? In fact, instead of running along the x-axis, this is going to be a line that runs along the y-axis. Okay, so let's do this. We're going to look at the limit as x, y approaches 0, 0 along Michael's C2 curve. Okay, so you guys do that. I'm not doing it. You do it. You do it. You guys work. You watch me. Now you fish. Grandpa fished that first space curve. You guys are doing the second domain curve. Is anybody done? Did anybody get a limit? Did anybody get a limit? What limit did anybody get? What limit did anybody get? Cameron? You got 5? Did anybody else get 5? Did anybody else get 5? And so the limit is in fact 5. Now is it okay, guys, if I work it? Is it okay if I do that even though you've got the right answer? Is anybody else happy that I can do that? So let's go ahead. Who's the C? Who's the C that works to hit actually the point 0, 0? Who's the C along Michael's space curve? It's again 0, and oftentimes it's 0 in these homework kind of questions. Now wherever I see an X, I'm going to put a, wherever I see an X now, I'm going to put a 0, and wherever I see a Y, I'm going to put, Michael said let's put in a T, and so if I do that, I would get a 5t to the 4 over t to the 4, and then I'm going to get cosine of 0, but cosine of 0 is 1, and so we get the limit as t approaches 0 of 5, which is the number 5. So do all the space curves, the limit along all the space curves, the limit along all the domain curves, does it go to the same number? Does the limit along all the domain curves go to the same number? So then what can we say by that theorem? What can we say about that theorem? The limit does not exist. This limit in general, this two-dimensional limit does not exist. I've got to ask, guys, is that easier than using delta epsilon arguments? Is that easier than making a delta epsilon proof? And if you guys didn't make delta epsilon proofs in Math 235, shame on your instructor. These guys know that beating. They've been through that beating over and over again. They're like, thank goodness, thank goodness. But guys, we're using limit tools over and over here that were proved. I mean, at this point, we're using limit tools that were proved with delta epsilon arguments. Okay, here's one of your homework questions from tonight's homework in 14.2. There's one of your homework questions. Do you think you could do that? Do you think you could do that limit? Look at that limit. Look at this limit up here. We're looking at the limit as xy of the function x squared y cubed minus 4y squared. It's homework. Why don't you do it? Do your homework. I'm not doing your homework. It's homework. I guess we're doing it in class, so it's not homework. We're cheating. many people are done? How many people are done? How many people are done? What did you guys get as the limit? What did you guys get? What did you guys get? What did you get for a limit? Anybody get a number? What did you get? What? Sorry,
56.
56. Did anybody else get the number 56? And you're like, what black magic did they use? What black magic did they use? Just plug it in. How many people recognize there's no division? There's no problems at all with division by zero there. This isn't a natural law. Do you have continuity? Do you have continuity? So wherever you see an x, you can just put a 3. And whenever you see a y, you can just put a 2, and you'll end up with the number 56. You'll end up with the number 56. So this ends up being 3 squared times 2 cubed minus 4 times 2 squared. And there's where your 56 is coming from. So you did your first homework question. How many people understood it? Who's your BFF? Continuity. It's like my buddy Seth Wood when I was a kid. We lived in a neighborhood, and there was my enemy, Dave Budd, who lived across the street. And he was a year older than me, and I don't know how many times I got beat up by Dave Budd. And I was like my dad. My dad was like a discus thrower in the Olympic trials, and I'm just like, Dad, I'm getting beat up. And he's like, as a Marine would say, you got to take care of this situation yourself, son. And I'm like, okay, have you looked at me, Dad? You know, David Budd's mother convinced him to have a vasectomy when he was 18 so he would never reproduce. I'm like, what mother does that? But after knowing David, I'm like, well, that's probably not a bad idea. I don't know. David would come out with his dad had all kinds of guns in the basement. His dad was kind of strange too. Big Civil War buff, but enough. So I just said, okay, Dad said take care of myself. So my buddy Seth Wood, who was shaving in 4th grade, was 6'3". I'm like, Seth, man, okay, I've got lunch. I'll give you extra lunch if you just make sure David doesn't beat on me. So we got off the bus, David came after me, Seth stepped in, David looked at him, David looked at me, I looked at Seth, and that was it. It was over. I'm like, Dad, I'm not sure that's what you thought. I kind of thought you might think I'm going to get my bravery, but I'm like, no, I'm going to buy a friend. That's what I'm going to do. And this is like continuity. You're like, I'm up against it, continuity. I don't know what to do. I don't want to delta epsilon. Continuity. Just plug it in. Continuity is your BFF. Okay, let's look at another one. Okay, this is one. It's one of your homework questions. I should probably tape some of the stuff I say. Okay, this is one, and I'm going to give you a hint. You can show that it does not exist. This book loves these problems just going to 0, 0. The numerator is x to the 4th, 4y squared. The denominator is x squared plus 2y squared. Now, where does the numerator go? 0. Where does the denominator go? 0. So you're like, crap. So try to find two space curves. That you can run along that might give you different numbers. Okay, give me two space curves that run down in the domain that you think you can get two different answers for running along them. What's your first space curve? What's your first space curve? Stuart, do you have one?
I have T and 0.
T and 0 is not, T and 0 is a good choice oftentimes. And how about another one? How about another one?
0T.
0T. Now let me tell you, it's not always gonna work. It's not always gonna work. You're gonna have to sometimes pick cleverer ones. But I don't have time to actually do the limits, so let me just do them quickly heuristically. If you plug in T0, wherever you see an X, you're gonna put a T, and wherever you see a Y, you're gonna put a 0. So if you do that, they're gonna go away, and you're gonna be left with T to the 4th over T squared, which is like T squared. What would your C value, Stuart, for that? 0. So as T goes to 0, where's T squared going to go? 0. So one limit will go to 0. Now if I look at 0T, these guys are going to go away, and I'm going to be left with minus 4T squared over 2T squared, which is going to go to minus 2, and that limit's going to go to minus 2. You see how Stewart's curves are going to work? You see how Stewart's curves are going to work? Okay, I want you guys reading and working on the homework in section 14.2. Okay, I'm going to start class on Monday with one that's just like this, but where the limit does exist. I want to show you that they don't exist when it's 0 over 0. And thank goodness they don't always don't exist. Thanks, guys. Have a safe weekend. Let's keep the dashboard low. It's Halloween. Let's keep the dashboard low.